You're going to need your hadron reference sheet for this, because to do these problems you have to be able to look up a baryon. There's no way by looking at a baryon. I mean, some of these have like an anti-sign over them, right? But look at this guy. This guy doesn't even have an anti. There's no way of knowing that that's the anti-particle, right? Okay, so we need to be able to look at this and say, is it an actual baryon or is it an anti-baryon? Okay, and so mainly this video is going to deal with everything south of this line here. Okay, so here are some conservation laws. Obviously, charge is going to be conserved. Mass energy is conserved, and this, by the way, is conserved for decays. I'll show you when, we don't have to worry about mass energy, right? Conservation of nucleon is sort of, right? But really, in general, the baryon number is conserved, okay? So this guy right here, okay, if you count up on in a particular nuclear reaction, if you count on what your baryon number is on the left side of the equation, the right side of the equation is going to have the same baryon number. We've never seen a reaction that violates conservation of baryon number, or at least the scope of this course does not cover anything that doesn't do that, right? Okay, so and this is super easy, right? Just baryons all have a number of +1. The antiparticle, these guys are going to have a baryon number of -1. Okay, so I think you've got some examples there. Let's look at these examples here, right? Let's look at the charge first. So this is +1. This is +0 equals +1 +1 -1, right? So charge works, right? We've got 1 on the left side, 1 on the right side. So charge is great, okay? Mass energy, well, we do have a little problem here. On this side, we've got 938 and 939.6, right? And we've got an extra proton here. The antiproton is going to have the same mass as this, right? So somehow we've come up with this much extra, not including the kinetic energy that these particles have, right? So the question is, where did that come from? Well, it's all good because this proton could be flying along with tons and tons of kinetic energy. Just accelerate it through 1 giga electron volts and you've got enough energy to do this, okay? Or accelerate through 1 billion volts and you've got enough energy to make a proton easy. So this is all good. Mass energy, if you have two things, remember that the proton can be flying along with a ton of energy and it can create particles. That's not a problem. So we're good here, right? But let's look at the baryon number. A proton is a baryon, so it's got a number of +1. A neutron is a matter baryon, so it's got a baryon number of +1, right? And then the proton is +1, and another proton is +1. There's too many pluses, right? And then, womp, womp, womp. An antiproton has a number of -1. So the left side has a total number of 1. Or the right side has a total number of 1. The left side has a total number of 2. So even though this balances charge, it never ever happens because we don't conserve baryon number. So no. Okay? So baryon number is not conserved. So to get these right, you need to tell me what law it violates. It either violates charge or it violates baryon number. The only time we worry about mass energy is this, okay? Is that if you have a particle that's decaying, let's say we've got a lambda particle and it decays, it can't create an omega. It can't create something more massive than it, but it could decay into a neutron or proton. It can decay into something lighter than it. Okay, so decays are basically, a decay is just you have one particle and it spawns a multitude of particles, right? Okay, that's a decay. In a decay, the energy of this can't be more than the energy of that. So just keep that in mind. All right. And if you look at this, these heavy baryons, they will decay into lighter ones because there has to be a baryon on the right side of the equation. So as they decay, they get lighter and lighter. The proton is the lightest baryon. If it decayed into something else, it wouldn't be a baryon. So therefore, the proton must be stable. This guy's stable. Notice that the neutron is not stable. So free neutrons actually decay. Their average lifetime is 887 seconds. And don't worry though. Neutrons in a nucleus are stable. Okay, if they're bound in a nucleus, they're stable. It's just free neutrons are not stable. It's interesting, right? So this is a decay of a free neutron. This is, by the way, these are the quark constituents. So a neutron is up, up, down, and 1 up quark, 2 down quarks, right? A proton is up, down, up, okay? And this is what's called a Feynman diagram. What's happening here, this is this axis right here is space. So it shows what the neutron is there, maybe it's moving to the right, and when it shoots off these decay particles, it's going to the left or something like that. We tend to draw them that way. And then this is time, this way, right? So you can see the particles decaying over there. This little thing here, this is the particle that mediates the exchange. In this case, it's a W minus. And it's kind of beyond the scope of what we're going to do is why that's a W minus that does that. Okay. The other thing that's interesting is notice that this is an anti-electron neutrino. Notice that the anti-electron neutrino is going backwards in time. Okay. And that's just a custom. That's just what we do in Feynman diagrams. Matter particles go forward in time. Antimatter particles go backward in time. I'm so sorry about your brain. I'm so sorry. Okay. So let's do some of these problems.